Let's look at the second example for shortest path. So this is also on Catis. The problem is called the slow leak. And this is one problem in last year's ICPC North America qualifier. So this is a kind of an open competition where many schools use them to select their team to compete in the ICPC regionals. And this is one of the harder problems in this set, I think solved by a relatively small percentage of people. So in the problem, you have a bike. You are trying to ride from, I guess it's from school to your home, but your bike has a leak. So while you ride a certain distance, the air will continue to leak out. So fortunately there are refilling stations in the town, where if you ride to one of the refilling stations, then you can refill your air, and the tire will have a full air, and then you can keep riding. So you're given the layout of the town, so where you are, what are the different intersections, and where are the refilling stations, and also the sort of D, which is how long you can ride without refilling. So the question asks to compute the shortest distance from school to your home, or alternatively, it may be that you cannot reach your home because of the flat tire. So let's look at two samples. So this is one sample instance. So this figure shows two sample instances. The first one, the school is here, home is here, and the D is 4 for the first one. So then the best distance is 12. Because it's 4, you can write into here, this location 2, and then you can refill, and then you can write to here, that's another distance of 4, and then you can refill, and then you can write here again, and then you are at home. So even though without considering the leak, the shortest path will be 5, 1, 4, so it will be 10. But you cannot take that, because you cannot write the 5 and 1, you cannot write the distance of 6 to reach this refill station to be able to go home. So let's look at the second instance, the second sample test case. So here D is 10, and there are 2 refill stations, one here, and as it turns out, you cannot you cannot reach home, so you're stuck. And the reason is even if you refill here, it will take 183 to get to this station, or 182 to get home. So it takes the distance 11 to get home, or distance 12 to get to this refuel station, but your D value is only 10, so you're stuck. So having understood what this problem is, let's look at the parameters. So the N is the number of intersections. So these are like the nodes, number of nodes in a graph. M is number of edges, or number of roads, and T are the number of repair stations. So this is specified which location are repair stations are specified in the input, and D is the initial instance that you can do. So if you start on a fully inflated tire, how long you can go. So that's the problem parameter. So essentially N is 500. That roughly means that the N cube algorithm would be acceptable, assuming that the constant is not very high. So I encourage you to pause and think about how to solve this problem. You may want to think a little bit longer, because this is actually a fairly difficult problem. But once we explain how to do it, hopefully you will find it actually quite feasible, not that hard. Okay, so the standard solution is, let's first understand the reachability among sort of the important points. which are the repair stations, and also school and home. So because we need to go sort of hop from the school, we either go to home or we go to one of the repair stations because we need to refill the air. So, and we can only go so long before we need to refill the air. So then the shortest distance between every repair station and also the school and home will be important. So so then because that's important, we can first compute that. So this is sort of computing all pair of distance, but we really care about the distances between the repairs among all the repair stations and including school and home. So after we've done that, then we can ignore all the other nodes. So then all we care about is the repair stations and the school and home, and then we can throw away any distance that is bigger than d, because that is the path we cannot take. So after we prune that away, then we sort of get a simplified graph where each node is either the school or the home or a repair station, and the distance between them is always less than or equal to d. Then it's simply a shortest distance problem. So that's the solution idea. And here's the code using Floyd washer. So I think there are 2 slides. So because here the possible distance is long, so I use this. The maximum distance is a long integer. So these are reading in the data, and remember t is the number of repair stations. So add 2 are for the school and home. So those are the important points. I sort of will map the original node ID and put them in take the repair station's node ID, put in this array repair, and then I will use the index into this to represent this new graph. So we read in the repair stations in the line here, and also because the encoding in input is starting from 1, and here I use starting from 0, so I need to subtract 1. So, and in addition to the ones that are read in, I also need to add the 0, which is the starting position, the school, and n-1, which is represent the home. So then I sort this. So then these are sort of all the important points that I care about. So then the next part is setting up to use Floyd washer to compute all pair distance. So I set up an array, 2D array SD, which will be used in the Floyd washer algorithm. And then I initialize it so that it first put max distance into every value. And then for every edge, I initialize that into both SDUV and SDVU because this is undirected graph. And also I initialize the II to 0. And then I call Floyd washer. So essentially, inside this FW are the 4 lines that does this Floyd washer computation. So after that, I have computed all the distance between every pair of nodes. So now I will construct a new graph. Where the number of nodes is nn, which is t plus 2. So the number of repair stations plus 2. So I'm basically going to do Floyd washer again because even though this is at this point what I want is a single source shortest path. So I want to know from the school what is the shortest distance to home. But because I already have Floyd washer set up, and Floyd washer is efficient enough for this, so I'm just going to call Floyd washer again. But I first need to set up the distance matrix. So this is sort of the new distance. Initially, it's everything is first set to default value, max distance. And then I will set up for each edge. So for every I and every j, I first extract the i's station and the j's station. And then I compute, so that I find the node corresponding with the i's and j's station. So U and V are the node IDs in the original graph. I and J are the node ID in this reduced graph. So if the distance I have computed for U and V is less than or equal to D, then that means that is an edge I can use. So I put this here. So here I didn't initialize every II to 0. So maybe that might be a problem. So I maybe when I copy the code and edit it, that was removed. No, I think that should, yeah, this should be okay without initializing that. This will be okay if the source and destination are different. Yes. So long as because in this case the source and destination are different, and we only query this is correct. But if we are querying the distance between a node and itself, then that will not be correct. So we may have something bigger than 0. So this is okay because yes. So because any paths that involve one or more edge will be okay. It's the passes that involve 0 or more edge that will be problematic. Okay. So yeah, after setting this up, we just call Floyd washer again, and then we simply query what is the distance from the first node, which we know will be the school, and the last node, which we know will be home. So then based on that value, we will print the output. So we are going to discuss another way to solve it, but I want to stop here, and that will be in the next video.